So last time I left you with the definition of the joint probability mass function of two discrete random variables. We could previously make sense of two discrete random variables on the same probability space. So this really just is notation. But we will have an example today to show you that it's a little bit more interesting than a way to define the independence of discrete random variables. That's the other definition that we had last time, and which we used on one occasion to represent a binomially distributed random variable as the sum of n independent Bernoulli random variables. Now, the other concept we had last time was the concept of expectation, and we are going to explore some more of that as well today, and particularly in the context of the law of total probability, which allowed us to calculate probabilities of events from conditional probabilities of that events given a partition of other events. And today we are going to see that expectations can be similarly calculated as expectations, conditional expectations of the same random variable given a partition of events in a formula very similar to the one that we have here. Okay, but going back to that definition of expectation, it's a little subtle because of that condition that we had to put that this series is finite. And I'd just like to introduce some terminology here that makes us write somewhat fewer series. Terminology. So I want to say that the series that we want to define, which is of the form that we are summing some function g of x over all x in the image of x, so in the context of a random variable, and I want to say that this or such a series converges absolutely if the associated series that you see there with the absolute value signs around the little x, or in this higher generality where the series of absolute value of g of x is finite. Okay, so it's all about the absolute value signs that we don't want in the object that we want to define, but that we need in the condition in order to make sense of that object in sufficiently high generality. So that means that it's really about these absolute value signs in here that we don't have in there, but we can replace this condition by saying if this series or sum converges absolutely. Okay, it's just a way to express in words what the series expresses. And it's terminology that is consistent with what you're going to use in the analysis course. And so that is another incentive for us to be using this terminology. Now, back to the first point that I recalled, the joint probability mass function. So in the context of two random variables on a single probability space, you now have several mass functions. You've got the probability mass function jointly for x and y, and you've got them separately for each x and respectively y. So in that context, if we have xy with joint probability mass function p xy, in the sense defined up there, we're defining the so-called marginal probability mass functions as, well, the probability mass functions of those random variables, so that we can write in two ways. But let me first write marginal distribution of x, and this is given by the p sub x of little x, which we've already introduced as the probability of x equal to little x, and which we can now write as a sum over all y values in the image of y, so the possible values for the random variable y, where we are summing over the joint probability mass function evaluated in x and y. So this is a way to relate the previous notion to the more recent notion of a joint probability mass function. And similarly, the marginal probability mass function of the random variable y is the probability mass function of the random variable y, but in this context, we can represent it as the sum over all x possible values of capital X over the probabilities jointly for x and y to take the values little x and little y. Okay, so that's terminology that we will use, and it's just pointing out how joint and marginal probability mass functions are related in general. Now here's an example. In this example, I take the simplest possible case of two random variable x and y, which both only take two possible values, namely 0 and 1. And so that means they are both Bernoulli random variables as we defined last week. So we can now specify a probability mass function, a joint probability mass function. So suppose that is given by something that I write in a little table. So we write, maybe start here with pxy of 0, 0 being 1/3, then pxy of 1, 0 being 1/2, then pxy of 0, 1 being 1/12, and pxy of 1, 1 being 1/12. Then what we've defined is that we can take the column sums and the row sums and find the marginal probability mass functions. So here, if I sum over the rows, that means I'm summing over all x's for a fixed y, and so I'm obtaining py of 0 is equal to 1/3 plus 1/2 is 5/6. And if I do the same in the second row, then I get the py of 1 as being equal to 1/6. And if I sum the columns instead, then I'm fixing the little x value to be 0, and I'm summing over all possible y values, and that gives me px of 0 as 5/12 and px of 1 as 7/12. Okay, of course you can also sum across the final column or the final row, and you will have summed all members, and remember this will always give us 1 as we sum over all possibilities for the random variables x and y to take values. Now let's look at this definition of independence of two discrete random variables. What we've said is we require the probability jointly for x equals x and y equals y to factorize into the probabilities of x equal to x and y equals to y. So we can now investigate this. We can now say, well, is the joint probability of x equal to 0 and y equal to 0 the product of the probabilities respectively of x equal to 0 and y equal to 0? And in this particular instance, the answer is no, because 5/6 times 5/12 is definitely not 1/3. Okay, so here pxy of 0, 0 is equal to 1/3, which is not equal to 5/12 times 5/6, which is the product of px of x times py of y. And, well, I've written it in terms of the probability mass functions here, but the meaning, of course, is precisely that of what appears in the definition of independence of these random variables. So we have these factorizations. Well, I write x, but x is 0 and y is 0. So probability x equals 0 times the probability y equal to 0 here. Conclusion is that we only need one counterexample to say x, y are not independent. Indeed, thank you. Okay, so this is, of course, a simple example. In fact, dependent random variables, well, either they have a particular construction from independent random variables, or they are somewhat simple in our examples. But, of course, in general, if you write down arbitrary functions on a probability space, you will find that independence is the exception of what you will find. But, yeah, I mean, for our purposes, independence is the nice concept that we are usually happy about, and dependence, as here, is what we can handle as well. Okay, so what more? I said the law of total probability was going to feature again today in the context of expectations. So let's look at conditional distributions. So here's a definition. In the context where we have a discrete random variable and an event, we can look at the conditional distribution of the random variable given the event. So the random variable is a function of a sample space, and of course we suppose it is a discrete random variable in the sense that we have defined, and B an element of F. If we want to condition on it, then we suppose that it is such that the probability of B is positive. So what are we going to condition? Well, we are conditioning events associated with a random variable capital X on the event B. So we then define the conditional probability mass function of X given the event B by what you might expect, but here's some notation as well. P sub X given B in an index evaluated at little x, it's a function of little x still, is the probability, let me first write the conditional probability of x equal to little x, conditionally given B. And that, remember, is the ratio of the intersection, probability of the intersection, that is the intersection of the event x equal to little x with the event B divided by the probability of the event we are conditioning on, which is B. Okay, that's something that is naturally called a conditional probability mass function. What you can now check is it satisfies our usual constraints for probability mass functions. As you sum overall values little x, this adds to 1. And as you notice, these are also non-negative. So we do have a probability mass function here in the original sense of that word. And because it is a probability mass function, we can look at our definition of expectation and say, well, the expectation is something that is a sum over all possible values weighted by their probabilities. Well, that applies if we plug in a conditional probability mass function. And so the concept we obtain is what we refer to as a conditional expectation of x given the event B. And so we denote that by expectation of capital X given B. And we do what I've just said. We sum over all possible values in the image of X. And what we are summing is X times the probability that X is equal to X given B. Or if we want to use the notation that we've just introduced with a conditional probability mass function, that's of course what you see here. It's P x given B of little x. And as with all of these, we have to say, provided that this sum converges absolutely. That is, if we put absolute value signs around the x, we get something that is finite. Okay, so now we have ingredients that allow us to make sense of a law of total probability, where we are expressing now an expectation of a random variable by summing over all members of a partition and now expectations of the random variable conditionally given each of the bi's multiplied by probabilities of bi. So here is the law of total probability for expectations. So if bi in f, I in I is a partition of omega with probability of bi positive for all I in I, then we can write the expectation of x as a sum over I in I of the conditional expectations of x given bi multiplied into the probability of bi. Okay, whenever the expectation of x exists. Right? That was another way of saying whenever these the sum behind the definition of expectation of x converges absolutely. Well, that's a theorem. Let's prove this theorem. It's the first of several theorems today where we have to handle sigma notation for sums in a way that, well, we will see several sums appearing here. So let me go into this and then get back to that comment. So the expectation of x by definition is the sum over all possible values little x of x into probability x equal to x. Now that is an event that we can call A, and to which we can apply the law of total probability. So this then gives us a sum x in the image of x multiplied into a sum over all I indexing our partition of conditional probabilities of this event x equal to x given bi times probability of bi. So let's just acknowledge by the law of total probability. So what can we do here? Well, this is where we need some skills of handling the sigma notation, where we can say, let's just put the sums up front. Is that what I want to write? Well, I have now, so let me continue. Just x into probability of x equals x given bi, probability of bi. Where do we want to go? We want to see the expectations of x given bi on the right-hand side. So what is that? That's the sum over all x of little x times the probability of x equals x given bi. So what's in the way is this sum and this probability. So what we're going to do is we are going to interchange the order of these sums so that the I sum comes first. And then we notice that this probability of bi, we can actually move that up front as well and write probability of bi as something that does not depend on the little x that's being summed over in the second sum. And what we are left with is the second sum summing over what remains is x times the probability x equals x given bi. Okay, and this is, by definition, the conditional expectation of x given bi. And we are seeing exactly the expression that I claim is the representation of the expectation of x. Okay? So like with the law of total probability, the question arises, why is this useful? Aren't we making a mess of things by writing a simple probability as a sum over many more complicated objects, in this case, conditional expectations, that maybe you feel will be harder to calculate than the expectation itself? So here's an example where actually there are some symmetries that can be exploited that help us. Remember, I defined expectation and gave you several examples of expectations of random variables with given distributions. What I did not include is the geometric distribution. The geometric distribution, remember, has probability mass function px of k equal to 1 minus p to the k minus 1 times p, for k equal to 1, 2, 3, etc. And what we want to also remember is that we can find a geometric random variable as the first success in a sequence, or so let's say among events A1, A2, A3, etc. Of Bernoulli trials. Right? These are independent events with identical probability p. And so with that representation, we can think about how we can relate the expectation of x to some interesting events. So one event, if you are thinking of doing this one step at a time, you have a first trial. Does A1 happen or does A1 not happen? Well, that's the same question as asking, is x equal to 1 or is x not equal to 1? And that's our event B. If we condition on that, then things are not so complicated, because the probability, so the conditional expectation of our random variable x given b is a rather degenerate object, because given b, this random variable is always equal to 1. So what we've defined in our conditional expectation is just naturally 1. On the other hand, if we want to apply the law of total probability, we need a partition, and the partition I have in mind is the partition into two events, b and b complement. So we will also need the expectation of x given b complement. Now what is that? Well, think of these trials. You will have a first trial. On this event, the first trial has been unsuccessful. So we have one for the first trial, which did not lead to a success. And the total number of trials that we have to wait is this one plus, we are taking expectations as well, some x tilde, which is looking not at the full sequence of events, but looking at the events A2, A3, A4, etc., and is asking what is the first success in that sequence. And that x tilde, which is the first success among A2, A3, A4, etc., this is again geometrically distributed with the same parameter p as what we started with. Okay, so I wrote tilde because the random variable is different, as it's related to a different sequence of events, a subsequence in fact, but the distribution is the same. So I get that this is also related to the expectation of x. Now, if you put this together, then we find that we have an equation from which we can work out the expectation of x. Let me just write one more detail for this formula to apply. We also need the probability of b, but b is x equals 1 with probability p. And so, so that's our final ingredient. So we can say, by the law of total probability for expectations, the expectation of x that we want to work out is equal to the probability, or I wrote expectations first, let me keep that order, the expectation of x given b times the probability of b plus the expectation of x given b complement times the probability of b complement. All of these we've worked out. The expectation, conditional expectation is 1. The probability is p. The conditional expectation here is 1 plus the expectation of x. And the probability is 1 minus p. Okay, so that is something where we have expectation of x on the left-hand side, expectation of x on the right-hand side with a different factor. We can solve for the expectation of x. So we rearrange to find the expectation of x times p, because 1 minus p are on both sides, so we are left with p on the left-hand side, is equal to the only term that remains here. Well, it's a p plus 1 minus p, so that is 1. Okay, and we want to conclude the expectation of x is 1 over p. Okay? There's only one problem with this. If the expectation exists. Do we know if this expectation exists? Do we know whether the sum defining this expectation of x is finite? At this point, we don't. So what I have to write here is if the expectation of x exists. Okay? And there's still important progress here, because it's a calculation that gives us an exact formula, provided only we show that the sum defining the expectation is finite. And certainly in the analysis course, you will learn that it is much easier to check that a series is finite than to work out the precise value of a series. And in that sense, it's progress. There are other ways also of calculating this expectation and of, in particular, showing that it is finite. And we will get back to that at a later stage in this course when we have some more techniques associated with expectations of random variables. But for now, I'd really like to have that warning on the page, and something that you may just want to think about when you find similar situations where you want to solve for something that you may actually not assume is finite. Okay, so what more? Expectations of random variables. Sometimes it's useful to not just have the random variable itself and its expectation, but some other expectations associated with the same random variable. So here is a theorem which says that if you have any function h from the real line into the real line and a random variable x, then we can form a new random variable by applying h to that random variable x. So how does that work formally? Well, random variables are functions on a sample space. So I'm defining z of omega to be h of x of omega for omega in omega. Well, we will write z is equal to h of x. And in fact, the way of thinking of x as just a real number, a random real number, you naturally apply h to that random real number. So that is the meaning that this composition of function captures. Well, the statement I'm making here is if x is a discrete random variable, then this z, so defined, is also a discrete random variable. And I said this was about expectations, so what can we say about the expectation of that new random variable h of x? So that can be written as a sum over x in the image of x of h of little x times the probability x equals x. Okay? Something very natural. If you think about what we are trying to do here, we're trying to work out the average value of h of x's as each little x is weighted by the probabilities of x equals x. And that's what this is trying to do. But we have a formalism, and the formalism says the expectation of a random variable is defined up there. And if this is a random variable in its own right, then this expectation is defined accordingly. We have to sum over all possible values of that new random variable z, and we have to work out the probabilities of that random variable z taking that particular value z that we are summing over. Right? So there is something to do here that is looking into how we set up random variables. But in order not to be drawn too deep into this at this point, I say the proof I'd maybe do it later. But the result itself, I'd like you to appreciate as a result that is available to you and that you hopefully find sufficiently natural to apply. So here is an example, or some examples, for what sorts of expectations associated with x you may want to calculate other than the expectation. So if you take h of x equal to x to the k for k greater than or equal to 1, then the expectation that we are looking at here is the expectation of x to the k, and let's just give a name to that. It's called the kth moment. Of x. Okay? And well, there are some other or related things that I'll get back to. If not today, then some other time. If we take x equal to x minus the expectation of x squared, then we will find the variance of x. So is something that relates back to things that we certainly care a lot about in probability as well as in statistics, as in describing not just what is our random variable on average, but also what is the spread around that average value that the random variable takes. But as I say, this is something that I'll do some other time, because for now I want to make use of the fact that I've got this general formula there, and that I can derive some other important properties of expectations from formulas just like that. So here is another theorem. Is that where I want to leave it, I wonder? I've been sloppy in a way that I didn't want to be sloppy. I've written more sums here. Those sums may or may not be finite, be absolutely convergent. So I have to say if this sum converges absolutely. Okay, so our context has been more than one random variable. So here I started with a function h that takes one random variable up there. Now let me take two random variables and have a function from R squared into R. Then the same formula holds if I want to work out the expectation of h of x and y. Then I can work that out by taking a double sum over all possible values for x and all possible values for y, where I'm just averaging the h of x, y over the probabilities that both x is equal to little x and y is equal to little y. Okay. And this time let me write it straight away, provided the sum converges absolutely. Okay, well, another theorem calls for another proof, but I'm definitely going to omit this proof. It's going to be similar to the other one, right? The results are effectively the same. You have more sums to handle, but in fact, this other proof, once you see it, addresses difficulties of multiple sums, where stepping up from that proof to this one will be a small step. As a warm-up, I'd like to do the next one as a result that I will prove, because that handles double sums as well in a way that is a little easier to follow. So here's a consequence. The consequence is linearity of expectation. So if I have two random variables, x and y, discrete random variables, and if I have a, b real numbers, then what I can, well, let me say random variables whose expectations exist. Well, in that context, I can relate the expectation of the linear combination of these random variables to the expectations of the random variables. It's just the linear combination of the expectations of the random variables. Okay. And the same is true what I said earlier. This is a random variable in its own right because it's a function on a sample space, and the definition of its expectation is what it is, going over all possible values for that linear combination. But that's not the way that we need to approach it now, because we have a more powerful theorem here that allows us to bypass being explicit about what the possible values of the linear combination are. So here, how do we apply that result? H of xy, if it is to give this, has to be h of xy equal to ax plus by. Then the theorem above, or to the left actually, yields that the expectation of ax plus by that we care about is equal to, in the notation of the theorem, the expectation of h of x and y, and that we can write as a double sum, no more space, as a double sum over x in the image of x and y in the image of y over h of x, y into, let me write p x, y of x and y here in my concise notation with the joint probability mass function. So that h of x, think of it as ax plus by here. So what we then can do is we can say we've got these sums, and these sums can be applied separately onto the first term and onto the second term. And splitting this apart in this way is giving us two sums where we can furthermore move some constants outside. Okay, so that gives us a times a sum x in the image of x, y in the image of y, of the x times pxy of xy plus b times the double sum x in the image of x, y in the image of y, y times the px y of xy. Okay, so what do we see here? Well, we see here that this x does not depend, it's constant in the second sum. So we can move it out of that sum. And what we then see is that what remains, namely this sum and this probability here, that's why we related the marginal probability mass function to the joint probability mass function. So this sum is equal to p, what are we summing? We're summing y, so we are retaining px of x. And the other sum gives us the expectation. So we find a times what you recognize as the expectation of x, right? So that is the sum here with the x, and that term, that's our definition of the expectation of x. And we have a similar term here, which you can handle similarly after interchanging your sums. You will find that is b times the expectation of y by exactly the same argument. And that's what we wanted to show. Okay, so what have we done here? We've written out our expectation as a double sum, and then we've used rules for sums. If a sum is over a product where one term does not depend on what we are summing over, we can move it outside. And that's otherwise leading just to the relationships between our joint mass function and the marginal probability mass function, and then to the expectation of x. Right? So everything then breaks down into quantities that we are familiar with, or at least that have appeared previously. Okay, so here are some consequences. Remark. So first, if A is equal to 1, B is equal to 1, then we get that the expectation of the sum of two random variables is the sum of the expectations of the two random variables. B, if one variable is constant, then what we find is that the expectation of ax plus b times constant 1 is equal to a times expectation of x plus b. Or inductively, you can establish that the expectation of a linear combination a1 x1 plus etc. plus an xn will similarly be a times the expectation of x1 plus etc. plus an times the expectation of xn. And finally, note that we made no assumptions about independence. Okay, so that's a couple of consequences, just picking up on what we've discussed. I hope you're happy with those. But what's all this good for? So one way in which this is useful is what you'll see on the problem sheet at some point, which is there are different ways of working out the expectation of a binomial random variable. And one way would be to use our representation as a sum of independent Bernoulli variables. Well, independent doesn't seem to matter, but certainly the representation gives you an easy way of working out that expectation, which you can compare with the definition, which involves binomial sums and some rearrangement necessary. Right? It's best explored by yourselves as part of the problem sheet question. But what I'd like to point out here is really something to do with that independence. Now, here's an example which is maybe not the most useful example, but that's not the point here. So imagine you have a spaghetti bowl and lots of strands of spaghetti with two ends each, and you want to tie them together at their ends. Right? The way you do that is you pick two ends out of your bowl. Suppose the bowl has n strands. Pick two ends and tie them together. There's two possibilities. Either they are the ends of the same strand, in which case you form a loop, or they are the ends of different strands, in which case you just get a longer strand of spaghetti. Okay? Now, what's the question here? I'm asking, on average, how many loops are you going to form if you keep doing this until you have no more ends in the bowl? Right? So that's something. Let me just write that down and then see if I can get at least part way into a solution today. So here's the example. Your spaghetti bowl has n strands of spaghetti with two ends each. Well, I think that's clear. So at each step, you take two ends at random and join them. And you repeat until no ends remain. Question: on average, that's code for what's the expectation of the following random quantity. So on average, how many loops do you form? Okay, well, let's make some observations. There's nothing identically distributed here, so we definitely need to be somewhat more inventive here when we want to analyze this. So let's suppose that we have k n's remaining. What is the chance that you form a loop the next time round? Right? You pick two n's at random, but the first one doesn't matter which it is. It's the second one that's interesting, because there's k minus 1 among which you choose, and only one of them is the other end of the strand you've already picked for the other end of. So that means that 1 over k minus 1 is the chance of a loop at the next step. And the other observation is, what happens? Well, the number of n's changes, right? If you tie two n's together, no matter which case you're in, whether you form a loop or not, the number of n's drops by 2. Okay, so what does this give us in terms of random variables? Let us look at the steps, n steps for n strands. Losing two n's each time. I denote by x equals 1 the event that we have a loop at the ith step. And I denote xi equal to 0 otherwise. Right, from what I've said, then I have xi Bernoulli distributed because it's 0, 1 valued, and we know what the chance of forming a loop is once we work out how many n's we have for the ith step. And putting that together, you will realize that the k is equal to 2 into n minus I on the ith step, and so we add 1. Well, maybe it's 1 out, but I think, yeah. Because I start summing from 1, we get this, this denominator here. And, well, we can now work out the number of loops, because all we need to do is count the ones in our sequence. So that is just summing the random variables x1 up to xn. And we are interested in the expected number of loops by linearity of expectation. This is the expectation of x1 plus etc. plus the expectation of xn. And now you can write that more or less nicely. With a bit of change of indexation, you will find that you are adding all the reciprocals of the first n odd integers as the answer here. And I'm sorry for running over time, but I think this is a way where we can usefully stop, because it's an example where we haven't thought about independence, and it's good we haven't, because asking whether those xi's are independent is maybe a question that's harder than answering the question about the expectation of this number of loops. Anyway, thank you for today.